All right, welcome back, you guys. I was going to put together here a video that was a quick review of some of the main points that we find in Chapter 7. So here we go. First things first, work done by a constant force. And there's just a couple things to keep in mind about this. This is 7-1, by the way. We have any object, whatever it is. Let's say this object will move a certain distance, and while it's moving through this distance, it's going to have some various forces may be applied to it. So if we were to look at a free body diagram of what is going on, then this object might be sliding on a surface, and it's got weight in the downward direction, and this object will have a normal force in the upward direction. But let's say we're pushing it along. There's some sort of applied force. And if this is it, if this is all that's happening, maybe it's a smooth surface and there's no friction, nothing hampering its motion, then what we have right here is an unbalanced force. And it turns out that any force like this that is unbalanced is going to be equivalent to the net force. And that's kind of an important distinction to make. So we have the force that is in the same direction or parallel to the direction of travel, and this force is not being canceled by anything else. Now, even if it were, there would still be some work done by this force, but we have work done by the net force in this case, and it's a very simple equation: work equals force times distance. Cool. These other forces, well, they don't play a part here, not because they cancel each other out. They don't play a part simply because they are perpendicular to this distance, and they have no component in the parallel direction to this distance traveled. So that'll be our next thing we'll look at. Work by a constant force, but work by a force at an angle. Some angle where it's not exactly parallel to that distance traveled. And this is still 7-1. What we might have going on is, let's take a look at the same sort of scenario. Object traveling a certain distance, and in this case though, if we're going to look at a free body diagram of what's happening to the object. There's our object. We might have a force applied in this direction. And so what that's going to give us is I got it dead. Let's try this one. A little nicer. We have a component of this force that is in the positive y direction, and we will have a component of this force in the positive x direction. And in this case, we understand that this angle right here, we call that angle theta. That angle theta looks too much like a 10. There we go. That angle theta really does something for us. We know that the work is going to be equal to the part of the force that is going to be parallel to the distance traveled. In that case, is this component. Well, this component has a value of force, if there's our force. Force times cosine of theta. So the force here doing the work on the object must be in the direction of the travel, so it must be this guy. And that's where the cosine theta comes in the equation. Now it's usually just moved to the end of the equation for us. And that's fine, no problem with that. But it's an important distinction that we want to make, where theta is the angle between the force and that distance traveled. And there's another point, a quick summary of what's going on here, what this means in terms of this angle. The work done by a particular force, it can be positive, it can be negative, or it can be zero. And that depends on the value of the cosine of that angle. So keep that in mind. We might have positive or negative work or zero work. For example, this vertical component, this component of this force in the positive y direction, is perpendicular to that distance traveled. Well, that means its angle to the distance is 90 degrees. Cosine of 90 would be 0. So we can get 0 work. Negative work. Okay, just a quick reminder about negative work. It does not mean that work has a direction to it. It just means that we need to keep track of a positive or negative sign here. We'll look at that in just a minute. So the next idea to take care of here is going to be the idea that work done is independent of the pathway that is used. So here's what this means. We might look at a situation. This is the classic example where we could try to get an object to a higher elevation by, thinking we're smart. We're going to use a ramp, and so the object will travel a distance d here that is parallel to the ramp's surface, and it's going to get there because we apply force to it. So what is going on in this case is we do a free body diagram. So much easier to do these things if you rotate your axes to be parallel to that surface. I kind of missed the mark on being parallel, but you get the idea. The weight of the object is still down. So here's our weight. We have a normal force here. And then our push, our applied force, will be in this direction. There's our applied force to get it up the ramp. And so how much work will we do? Well, we have to push just hard enough to overcome this component of weight right here. And so our applied force will equal that value. And if we look at an angle, I haven't defined that angle here. The ramp would have a particular angle, called angle phi. That's PHI, that's a Greek letter. Sometimes you'll hear it pronounced phi, but I believe the correct pronunciation is phi. So I'm not going to call that theta. I'm just naming it something else. We could have named it alpha, whatever you want. But that angle in this free body diagram shows up here, angle phi. And so this component here is going to be the force of gravity times sine of phi. Well, what that means, if we're just pushing hard enough to get it up the ramp, then our applied force must just overcome that, or just be equal to that. So our applied force is equal to this value. And we know that weight is just mg. So it's easy enough to do the substitution, and we can figure out how hard we have to push. Awesome. And with our applied force being parallel to the distance traveled, the angle theta between our force and our distance would be 0. Cosine of 0 gives us a value of 1. So the work we do, put down here, the work we do in this case, in this situation, we have our force, our applied force. But we've already said our applied force is Fg sine theta. Sine phi. Right? And we're going to so this is our force. That whole thing is just the force we're using. And we're going to multiply by the distance traveled. And to be technical, I'll put the cosine theta here. But you want to make sure you understand that theta is the angle between our force and our distance, and it will be 0 in this case. we could figure this value out. And we don't need to do numbers right now, but let's compare the situation. Let's say, you know, before we got real smart, before we did all this evolving, we would have just lifted straight up. Awesome. Well, so we get to the same height. We have distance traveled here. In order to do this, we have to apply a force. The force has to be in the upward direction. And if we look at what's happening in this case, we have weight of the object pulling straight down, and that's still just mg. But now, in order to get this object up that distance, we have to apply a force that is just enough to overcome that. So here's our applied force. And if it's just big enough, well, it's going to be equal to the weight, and it's going to be, therefore, equal to mg. But the distance will be much shorter here, so there's a bit of a trade-off. So we have the work done is equal to our applied force. Well, our applied force is just mg, and the distance traveled here, divided by that. And I'll go ahead and put the cosine theta here. No other angle to worry about. And again, our force is parallel to that distance, so the angle theta would be 0. So it essentially, cosine of 0 would be 1. It goes away, multiplied by 1. And it turns out that these two amounts of work are equal. It doesn't matter what pathway we take. If we take the long way and we get to use a smaller force, or if we take the short way but we must use a larger force, it's the same. So we could come up with a final statement that says, well, you know what, I'll call FG mg. I've got sine of phi, and I multiply by, I've got to call this distance 1 and distance 2. And I have to make that distinction because otherwise, you know, something terrible is going to happen. So I'm going to multiply, there's the force in this case, times d1. Cosine of 0 would be 1, so that can go away. So in this case, also on this side is equal to mg 2, and cosine of theta will be the value of 1 again, so it kind of goes away. So I have my force times my distance, and this is going to equal my force times my distance. I get a smaller force, makes it easier, but I have to use a larger distance in this scenario. I have a larger force because I'm lifting directly against gravity here, but I get to use a smaller distance. But the value of the work done in each case is the same. Okay, so that is how the pathway is going to affect what we're doing, and it really won't. Not in situations like this. More is coming on this later on in the next chapter, by the way. Okay, so the next idea, it's page 2 here. Next idea to work with here is the work-energy theorem. Super important idea. So essentially, there's a couple things going on. If you apply a force, according to Newton's second law, you apply a force to an object, and you will then produce an acceleration. The object's velocity will change. Well, that's only true if there is a net force acting on your object. Okay, so you could have whatever object, and you might have a force in the upward direction, you might have a force in the downward direction, you could have a force to the right, you could have a force to the left, and notice I drew those unbalanced. So in this case, there's a little bit here that did not happen, so there's about that much here that would be left over, that would not be canceled out. So I can see that this is going to be a net force, and any leftover net force will cause an acceleration in our object. Awesome. So we have an unbalanced force. Well, that's Newton's second law, and this totally relates to work, except that we have to think about the total amount, because if we have balanced forces, if I have a force this way and a force this way, and here and here, and everything balances, so my net force is 0, well, in that case, I would have, let's say this object is moving to the right, a certain distance. Well, I have work done by this force, and I have work done by this force, but this would be negative work, this would be positive work, and they would end up canceling out. So if the net force is 0, the total work done would be 0. Okay, well, what if it's not? So we're not going to consider that situation right now. Kind of boring. The total work done, though, if there is a net force left over unbalanced, is going to cause the kinetic energy of an object to change. So we see a change in kinetic energy. All right. Well, kinetic energy is the energy of motion. So work total is going to be equal to a change in the kinetic energy. That means there is a net force applied across a distance. But what we get when we talk about the energy, the kinetic energy, is 1/2 times mass. And since velocity is changing, we've got to have final minus initial velocity. But each of those values will be squared. Off to the side, just kind of real quick, kinetic energy. All by itself, this idea of kinetic energy of an object is just 1/2 mv squared. Okay. So keep that in mind. Just if you want to know the instantaneous kinetic energy, you need the object's mass and you need the velocity at that moment. But here we're talking about a change in kinetic energy. The motion must be changing. In order for motion to be changing, we must be seeing an acceleration in the object. And for that to happen, we have to have a net force that is non-zero. And so we see a non-zero net force multiplied by a distance, and we'll throw in the cosine of theta just because we want to be smart. And when this happens, there will be this corresponding change in velocity, which also we can describe this as a change in kinetic energy. You can distribute the 1/2 m to each of those if you like. It really doesn't matter. You'd have final velocity 1/2 m final velocity squared minus 1/2 m initial velocity squared. Doing work from an unbalanced net force, from a non-zero net force, will produce a change in kinetic energy, and that is seen or measured by looking at that acceleration, that change in velocity. So that is our work energy theorem. And consider this. When total work is 0, what do we see? Well, we see that the change in kinetic energy is 0. And no acceleration takes place. So the object will either continue at its current velocity or will remain at rest, depending on what it's doing. So there's our work energy theorem in a nutshell. Okay, last item for review. Page 4 here. This is going to be work done by a variable force. So if we, variable forces, okay, so this is much like springs. If we're going to look at the force applied, or that we must apply to a spring in order to stretch at a certain distance. And that by stretching it or compressing it, we change the position of that moving end. And typically we'll see this linear relationship. All right. So we can say that when the force varies linearly, as it does with many springs, then the work done is represented or is equal to the area under the line. Okay, well, the area under this line is simply a right triangle. The area of a triangle, we have 1/2 base times height. So the work done by this variable force is going to be equal to 1/2 when we're doing base times height, okay, or height times base, it matters not. Talk about the force and the distance traveled. Well, fair enough. This force is the force we must use to overcome the spring force, so it's really equivalent to the spring force. But if you remember from Hooke's law, spring force, the magnitude, if we get rid of the minus sign, the magnitude is just kx. So we can do a substitution. We have 1/2. Look at the magnitude of that force, kx, and we're multiplied by the distance traveled. So if we simplify, we see that the work done by this variable force is 1/2 kx squared. And this is, typically the work done by a spring or the work done on a spring, depending on how you're looking at things, if the force is applied to the spring or if it is a force that the spring applies to something else. And you can see that the force varies. The force would increase as the change of position increases here. Interesting thing going on that we see, a little, by the way, how about the slope of that line? Well, slope is rise over run, so we're going to have force divided by position. Well, that force is equivalent to the spring force, which is equivalent to kx. And our position is just x. And we notice those cancel out. So the slope of this line gives us the spring constant. Nice little relationship there. All right, that's it for the review. Next video will be to cover 7-4, which is about power, and that will wrap up this chapter. Thanks for watching.